Thank you, Yalda, and thanks everybody for attending today. This is the first in a series of webinars where we attempt to answer the question, what's in my NMR Tube, using tools available from ACDLabs. Before we go into the webinar, I'd like to just say a few words about ACDLabs. ACDLabs was founded in 1994 in Toronto, in Canada, and the headquarters are still there. We have sales and support offices in the UK, in Germany, in France, and in Asia. And for all the other regions, we have an extensive network of representatives that cover them. The company started initially with just 2 employees in Toronto, but now we have grown to have almost 200 employees supporting customers all over the globe. We have more than 4,200 industrial customers at 4,700 locations in 89 countries. And last year, we reached a milestone with more than 2 million downloads of our free tools. So we've been around for quite a while. Last year also we celebrated, 2019, we celebrated 25 years of the company, and we had a nice meeting in Spain. And here you see the group photo from that meeting, and you see all the people who are involved in creating the software that you are using. So it's quite an impressive organization if you consider that we are only dealing with software. And you can see here all the people involved in the development, in testing, in application support, in technical support, in sales, and in every other aspect of the company. The company started back in 1994, and the initial products were the carbon NMR predictor, the log P prediction, and a UPAC name. The company has grown quite a bit since then, and the current offerings can be divided in 2 main parts: the ACD Spectrus platform for all types of spectral processing, analysis, and data management, and the Percepta platform for PhysChem and ADME-Tox predictions. We offer full support for all major analytical techniques, including chromatography and LC-MS. We have ongoing collaborations with all the major instrument manufacturers to ensure that we correctly import the data generated by their instruments and keep our format support current. We can, and we have, through our professional services department, integrated our software with all sorts of analytical instruments so that we can retrieve the data once it's generated and manage it. We have moved on from interpreting single pieces of data to providing the facilities for total information and knowledge management in an efficient way. This leads to better support for making the right decisions in a time-efficient manner. And all these are done through the use of the multitude of options in the ACDLabs ecosystem. So today we're going to talk about, what's in my NMR Tube? And this is the question every NMR spectroscopist has to answer. However, the answer may not be that straightforward, and there are a few options for the answer. Some people would say that, yes, I'm certain, I know very well what I have in there, or they may say I have a good idea. In these cases, what is needed are the structure verification tools. These are the tools that will allow one to confirm whether what they are certain about is actually correct, or whether the good idea they have is good or it needs some fine-tuning. It would have been nice if these were the only options. However, in real life, there are 2 more options. The first option is that, I have no idea what is in there, but I know that it's not something new. I know that somebody else has done this before. So, I'm not trying to rediscover the wheel. In this case, you can use tools like our known structure search, which we'll talk about later, but this will allow you to find what could be in there that you have. The last and maybe the most dreadful option is that I have no idea what is in there. I just isolated it. And in that case, you need to use our very advanced tool, Structure Elucidator, and all the facilities in there. In this presentation today, we will focus on answering the question if one of the first three options are true. On the next webinar, in part 2, we will talk about structure elucidator. So let's start seeing what we can do for each one of these cases, and let's take the middle case one, the third case. And it's not something new. So in principle, what we want to do is what is defined as dereplication, which is, as the definition here says, the process of testing samples of mixtures which are active in a screening process so as to recognize and eliminate from consideration those active substances already studied. In essence, you don't want to replicate work that has been done before. That's why it's called dereplication. Dereplication is extremely important. Also, if you are doing things like natural product research, where you isolate something and you want to ensure that nobody has isolated the same thing before. But also, the same tools can be used in other applications, like, for example, in competitive analysis. You got a product from a competitor, you want to find what they have in there. Almost certainly, they have used compounds that are known. So yeah, being able to search for them will give you the answer faster. Very similar case is counterfeit analysis. If you got the product from somebody else, which is labeled, marketed the same name as yours, and you want to see exactly what they did, again, they have not used something different in there, something unknown. So the same procedure can be used to find out what is in there. Finally, in mixture analysis, you can use the same tools, because if you have mixtures of things that are known to somebody else, but they are not known to you, then again, the same logic can be applied. Now, how can you do dereplication? And the most popular method of doing dereplication is high-resolution mass spectrometry. It's very easy and quick. However, it will only give the molecular formula. So if there are several options for a given molecular formula, MS is not necessarily the right tool to use. You could do dereplication using proton NMR spectra. That's very easy and quick. However, it has limited information. Proton NMR spectra are just around 10 ppm wide, and all the information is squeezed in there, and it's affected by several factors like solvents, concentration, pH, and so on. The third option is to do some form of carbon NMR spectroscopy. This can be direct or indirect detection of carbon. It's more difficult than the others and slower, but provides much more information. So what are the real advantages of using carbon NMR spectra? To begin with, you have a very large dispersion. You have more than 200 ppm where peaks can appear. And even with these, within these 200 ppm, you can have you do have extremely narrow peaks. You can see here an expansion of a carbon spectrum. And we see that in the region between 164.5 and 165.5, so just 1 ppm. We have 1, 2, 3, 4, 5 very well resolved peaks. There is no question that these are peaks. Nobody will say that these are spikes or shoulders or whatever. And there is quite a bit of space for others. So in just 1 ppm, we have all this information, and we have 200 ppm where the information can spread. Quite information rich, as it's referred to sometimes. Another advantage of the carbon spectra is that you have minimal effect of solvent, concentration, and pH. These are things that can really wreak havoc in proton NMR spectra, because they may move the frequencies by even half or 1 ppm, completely distorting the spectrum. In carbon spectra, that's not much of a problem. If they did move even that much, it's nothing in comparison to the whole 200 ppm range. So yeah, you don't really need to worry too much. Carbon NMR spectra are almost magnetic field independent, meaning whether you record the carbon NMR spectrum on a 400 megahertz or on a 600 megahertz or on an 800 megahertz, the actual information you will get will most probably be exactly the same. The same peaks will appear at the same frequencies. You will have differences in the intensities resulting from the differences in sensitivity, but the 600 megahertz spectrum is not going to tell you something more than what the 400 megahertz spectrum did. This is extremely important because this means that you can work somehow field independent. You can mix and match spectra from different fields. The biggest also advantage is that carbon NMR spectra are very easy and accurate to predict. You can predict carbon spectra to very low accuracies, very high accuracies, down to 2 or 3 ppm only, and this is very easy to do. In contrast, for example, proton NMR spectra are notoriously difficult to predict to a similar level of accuracy because of all the effects that we discussed before. It's interesting. You can very precisely predict proton-proton coupling constants, but chemical shifts, you have some problems. So yeah, it's clear that carbon NMR spectra or carbon NMR information, because it's not necessary that you record the 1D carbon spectrum. You may record some 2D experiments like an HSQC and an HMBC, are the way to go if you want to do dereplication. And the way that the workflow will be is that you will record the carbon information, and then you will need to search for this information in databases. And there are a few options for databases. You can have either commercial or open databases, and you can have databases with either experimental data or databases with predicted data. And the difference between commercial and open databases is pretty clear. Commercial, you have to pay. Open databases, they are freely available to everybody with the advantages that we think of and we understand. I'm just going to focus a bit in the question between experimental or predicted databases. And one may say, may answer, without too much thinking, that experimental databases are better because they contain real data. This is true to a point, but there are quite a few implications. To begin with, they are limited in numbers of structures. I think the largest database with real data does not contain more than like 500,000 structures, which is not that a big number if you consider that databases of structures like PubChem contain a few million structures. So yeah, the experimental databases are limited in the number of structures. Usually also they are limited in low magnetic fields, they are limited in solvents, etc. So this may be a problem. Finally, and by far the most important, the fact that you have real data doesn't necessarily mean that you have good data. And you are better off having good data than having not so good data, obviously. And I'll show you here an example of an entry from one commercial database, doesn't matter which one it is. And this is the spectrum that's stored for this structure, and this structure has 24 carbons. The spectrum, the carbon NMR spectrum appearing here, has 54 signals, so there are 30 more signals, and that's obviously a spectrum which is a real spectrum. It's an experimental spectrum, but it's not the correct spectrum for this one because you have so many more signals. So what probably happened here is that either there is an impurity or a sample had been altered, decomposed, degraded, whatever. So here is the example where, yeah, real data is not good data. And, if you are trying to do the replication and you believe that this is the spectrum for this compound, then you have a few problems. The databases that contain predicted spectra, they contain spectra as good as the predictors that have been used to generate them. And if you are using ACDLabs predictors, we are well known to have probably the best prediction engines around. Databases of predicted spectra are also magnetic field independent, because you can do the prediction at any field you want, and in any case, you are only predicting carbon frequencies, which do not change with the magnetic field. The databases of predicted spectra can be adjusted for solvents. You can run your predictions in different solvents. You don't need to actually go ahead and record the spectrum. More importantly, these databases may contain up to a few million structures, depending on the structure source. So you just take structures from somewhere, for example, from PubChem. PubChem right now, I think, has close to 100 billion structures. You predict the spectra, and you have a database with up to a few million, way better than the up to 500,000 that any experimental database will have. This type of workflow is fully implemented into ACD Spectrus. And the way to use it is you have a little icon that will activate the known structure search add-on, which is available for Spectrus processor and NMR workbook, and is included, of course, in Structure Elucidator. This will allow you to search these extensive databases containing spectra, predicted spectra for all the compounds in PubChem. And it requires that you have carbon data somehow, obtained from any source and by any means. You can either have a 1D carbon spectrum and or an HSQC and or an HMBC, or you may have just a list of peaks. That still will work. And the way that it works is that once you press it, you are presented with this dialog, and you only need to define a couple of things here. So you need to define whether to allow excess signals in structures and whether to allow lack of signals in structures. So the case of allowing excess of signals in structures is to compensate for the case where you didn't observe all the carbons. For example, you may have not observed some quaternary carbons, so you didn't see them, but if the structure in the database has it, then that's fine. So you give a tolerance here. The opposite is if you have a signal in your experimental spectrum that does not appear in the actual structure, maybe because it's an impurity or something else. So here you define how much tolerance you have on this. If you are very confident that your carbon spectrum is correct, something like 1 and 1 is fine, but it's not uncommon that you will use higher numbers. The second part to define is whether you know the composition or the monoisotopic mass. Maybe you have a mass spectrum or you have the composition by some other means. If you have this, you can define them here, and this will speed up the search. Once you do this, you just click OK, and after a little bit of time, you get the result. So that's the first option. What happens if what you have in there is, as it's called, a known unknown. And that's how you can get the answer. If we look at the other options, so we are in the situation now where we are certain about what we have in the NMR tube, or we have a very good idea. And that's when we use our structure verification tools. So when do you have a good idea of what's in the NMR tube? If you know the reaction, I know the reaction and the possible products. That's a very good starting point, usually. Or I know most of the structure, but only missing a small part. Or you may say that, I have seen this structure before. All of these eventually boil down to the sentence that, I can propose a structure, or I can propose structures. And then what the software will do is it will take all your experimental spectra, it will take your proposed structure or proposed structures, and come and calculate the so-called match factor. For example, match factor 0.82 means there is an 82% chance that this is the correct structure for the spectra, or that these spectra are correct for that structure. Before moving further, I'd just like to take a little bit of time to talk about how this match factor is calculated. And the principle behind the calculation of the match factor is that you predict the same experiment types as the available experimental data. You see again, the spectral prediction comes into play. And again, you understand how important it is to have accurate predictors. So you predict what you have recorded experimentally, and then you compare the experimental spectra to the predicted spectra. Okay. The match factor will be calculated based on the biggest differences, and it is not based on an average of deviations. Okay, that's very important to say, to understand. One big inconsistency is sufficient to drive the match factor very low. So what does this mean? Let's say that we have a compound that should give, I don't know, 20 signals. We predict the spectra, and we find that 19 out of these 20 are spot on. However, the 20th is completely off. You can imagine, for example, you did an oxidation of an alcohol. You were expecting to see a carbonyl group appearing. You don't see a carbonyl group. The match factor is not calculated based on the average of everything. So having 19 out of 20 signals would have meant that, yeah, 95%, that's correct. No, this is not the case. You don't do it like that. If you have 19 out of 20, that's good, but the one that is off is enough to drive you to zero. So one big inconsistency is sufficient to drive the match factor very low. And this is something to keep in mind, that the match factor is calculated based on the inconsistencies, not on the agreements. Okay. Now you may say, yeah, I can do all these things myself, and I don't need software. Okay, because I've been doing NMR for I don't know how many years. I've seen so many things. So what's the advantage of using software? Well, there are quite a few good reasons for using software. Obviously, software will be faster. Usually, you can verify a structure within less than 5 minutes in the worst case. You can't necessarily do this if you are a human expert. This, of course, can be discussed quite a bit, but there are two other reasons that are far more far-reaching. And the one is that the analysis using software is completely unbiased, meaning that software doesn't know all of the background information that you probably know, and the software will not be biased to give a result one way or another as the human expert may be. So imagine that you are in the situation where you have a reaction and you know what you put in and you know what the reaction result is expected to be. It is in human nature to try to prove that everything worked the way it was expected. And doing this, you may oversee some problems and try to somehow make the data fit your expectation. This is not happening with software. Software is completely unbiased, and if there is a problem, it's going to report it without much hesitation. The other advantage of using software, like software from ACDLabs, is that you have at your disposal a much larger knowledge base. So there where the human expert may be quite good at identifying problems with particular classes of compounds, no human can really have the breadth of knowledge that is embedded into software like the one from ACDLabs. We have so many hundreds of thousands of compounds in our training databases that it's just impossible that any human would be anywhere close. So yeah, there are very good reasons for using software, and in the end, it all has to do with the whole idea of getting a second opinion. So if you gave the answer to the problem and you are maybe happy or not, you may go and ask a colleague of yours, and the colleague may point out to something that you have missed or not. Well, software does the same thing, but in a much more comprehensive manner. So you are better off seeing something that you like and having software agreeing with it than seeing something that you like and moving on without further confirmation. So it's quite important in any case. It's also important that, what do you do if you have multiple structures that have been proposed? In that case, the human expert will enter all these multiple structures. Alternatively, the software can generate isomeric structures starting from one of the structures. And this may not sound that important initially, but if you think about it, it is actually important because you need to verify against many structures to avoid a false positive. Because, imagine that probably you haven't collected sufficient differentiating data and you have more than one structures agreeing with the data sets that you have. You have a problem, you may have a false positive. And it's also important to avoid this thing. It's important to have C13 information and correlation information. So you need to have spectra like the HMBC and the COSY that will show you information about the carbon, but also information about the correlation. Where are these carbon signals close to? Again, this helps to avoid false positives. So all these factors are also important in order to ensure that you have a true positive and not a false positive or a false negative in this respect. So this is where the combined and concurrent verification tool comes into place. And what you do here is you have your spectrum and you have your proposed structures, and you get the match factors for all of them by defining, test concurrent structures and automatically generate isomers. And we see in this example that, the first structure got 85%, but there is another one with 73%. And 73% is a relatively high percentage, definitely worth investigating a little bit further. So, if we go now into the last case of all this, I'm certain about what's in my NMR tube because I've done this many times and I know very well how it behaves, or we've had independent confirmation of the structure, maybe by some other means. Maybe, we purchased it and the vendor gave us a certificate. In the end, you may be in the situation where you have a structure that you are not sure about because, what if something is different now? You've done it many times. What if something changed now? Or what if, for example, the supplier did not test sufficiently? And I would like to remind you here the case of botulinum, which was a drug that was in testing a few years ago. And botulinum was manufactured by Pfizer, but some researchers decided to use an alternative supplier. And it turned out that the botulinum batches from this other supplier were not actually botulinum, it was an isomer. And all that research that they have been doing more or less went down the drain because it was a different molecule. So you really need to be sure that even when you are sure that it's the correct one, you need to have further assurances that this is really the case. And that's when we have the option for what we refer to as unbiased verification, or UBV. And UBV will run a full computer-assisted structure elucidation instance starting from the spectra and extract the molecular formula from the proposed structure. If the structure found by UBV is the same as the proposed, then the structure is confirmed with the highest level of confidence. UBV is really the ultimate verification test. So UBV doesn't look at the structure at all. It only takes the molecular formula and tries to see what structures resulting from the spectrum will agree with this, will have the same molecular formula. Now, if you have the same as the proposed, then you are happy. So as we say, UBV is the ultimate tool. And this is the complete verification path. So initially the structure will fit a single NMR spectrum. Then the next step is that the structure fits NMR data better than similar isomers. And finally, the structure is confirmed by UBV, fits NMR data better than all plausible isomers. So that's when you are good. At this point, I'd like to move to the software and show you some of these things in action. I'm going to end the slideshow, and here we are on the software. And what we have here is we have a sample. We are exploring the first case I went into detail, the case where I'm not sure what I have, but I know it's something something known. So this is a sample that was given, and we were told that this is it's a mixture of pesticides. Okay, we don't know anything more about it. We only know that it's pesticides, and we see the proton spectrum, and it's obvious that there are more components in there because we see several different intensities. And if we go on the HSQC, we can isolate two peaks. We start with this one here and with this one here. And these are definitely peaks from the same compound because the intensity ratios agree. And then we can go to the HMBC. And if let me just zoom just a little bit here, we see that this peak correlates to 4 other peaks here. So we have 4 other carbons, and the peak from here also correlates to another one here. So it seems that we have enough information on carbon, and we can view all this information in our table of spectral data, and we see we have 8 signals for carbon. And that's more or less what we get, what we have at our disposal. Because it's an HSQC, we have information about multiplicity. And the question is, what could that be? So we know we have 8 signals for it. We know it's a pesticide. And we have also additional information. And the additional information is we have a molecular weight because we have a molecular ion. And we know that the molecular weight is 232. So we set our monoisotopic mass between 231 and 233. Unfortunately, we don't have a high resolution MS. So we just set the tolerance to 0.5. However, if we have 8 carbon signals, it's probably safe to say that we have all of them, and we just allow excess of one and lack of one signals. The actual composition will leave very lax, between 5 and 70 carbons and between 2 and 100 protons. So let's do the run and see what information will this give. So what is happening now is that the software took all these carbon chemical shifts and the monoisotopic mass and is searching this database of predicted spectra for the compounds that are in PubChem. So that's close to 100 million compounds, and it's searching through them, and we see that it is finding things. Now, obviously, a database with 100 million is not in a single file, so that's why it's taking a bit longer. And it says that now, 2 stereoisomers have been excluded. And if I click OK, we can see down here the results. And we can see that the best one appears to be this, and that's the second one. And let me zoom a bit here, because what we see here is we see at the top the query spectrum and at the bottom the hit spectrum. So that's the database spectrum, and that's our spectrum, which is not a true spectrum because we don't have a 1D carbon spectrum, but it's, let's say, an artificial spectrum synthesized from the frequencies that we had identified using the HSQC and the HMBC. And we can see that there is relatively good agreement for this one. Or if I go on the second isomer here, the second hit, we will see that the agreement is maybe better, and you see here things look better. It turns out that the correct answer was number 2, and we see here some metrics about the deviation between the mean deviation between the experimental and the predicted chemical shifts. So as long as these are less than 2 ppm, that's probably fine. And yeah, if we just go down on this table, we see some more. So yeah, we say that up to number 4, we have a very good idea of what could be. So the next step is that, yeah, we will go to search this for the more information about these actual molecules and see if any of them is a pesticide. And as I said before, yeah, it turns out that the second one is indeed a pesticide. And that's the correct one in there. So yeah, that was the first one I wanted to show to you. And this was, as I said, the answer to the first case that we examined. I don't know what I have, but I know that it's something known. Let's go to the next option. And the next option is that, yeah, I know what I have done. I have a good idea. So this is an example now of, again, a data set where we have almost everything. I mean, we have a proton, we have an HSQC, we have a COSY, and we have an HMBC. And we also have a proposed structure. And this is the structure that was given to us. However, if we go and try to do the automated verification, we see that things are not that great. We get a match factor of 0, not good. And yeah, all sorts of problems, contradicting correlations, several atoms are unassigned, and so on and so forth. So yeah, we did the reaction that we thought that we did, but things didn't work out correctly. And we see here from the color coding, we see which parts of the molecule appear to verify with the spectra that we have and which parts not. So we see that the top part here looks okay. However, down here, things are not great. We have a whole methyl here that it's missing and another CH here that's just not there. So yeah, what can we do here? We may assume that this is an isomer, and we may go and activate the option to test concurrent structures and automatically generate isomers. And I click to run the assignment, and the isomers are very quickly generated, but the result, let me close this thing, the result is not necessarily better. We get zeros. We see here how the isomers were generated. The red bonds indicate the changes that have been made, but not great, again, zeros. So what could we do here? There are a few things that we can try also here, and normally, under normal circumstances, the human expert will have to start thinking a lot what happened here. And however, we can use some of the tools here, and we can use, in fact, UBV itself, unbiased verification. And if I select unbiased verification, okay, it tells me it's going to use just the first structure, that's fine. And after a little bit, UBV shows me the proposed structure and tells me that, hey, you know, this part appears to be correct, and the rest is the question mark. And it's saying that, yeah, it's going to set up this fragment as a starting point and try to solve the rest of the molecule. So if I click OK, yeah, it's telling me that it's going to be an easy problem. And it starts running computer-assisted structure elucidation, and you could see the structures here jumping. And after a little bit, it tells me that the proposed structure was not generated. However, it generated 10 unique structures. So the best structure appearing here has a very high match factor, 0.96. Our proposed structure was at 0. We see that most of the molecule is green. There is another one at 0.91 and another one at 0.85 that maybe we may want to consider. But really what happened here is that the software very quickly and easily took us out of a potentially rather difficult situation. There where we had everything wrong, suddenly we have now just 3 structures that we need to differentiate about. And in reality, the first one, this one here is the correct one. For these other ones, yeah, you may do some additional experiments, maybe some nitrogen correlation experiments to confirm that, to confirm which is the correct one. So yeah, this is the case where UBV and in general, the ACDLabs tools showed us very quickly which is the correct answer. Yeah, so this was the case when it was something that we were kind of knew what it was. And I'm just going to close this and show you the last example, which is an example of a very well-known molecule. And we are talking about strychnine. And let's say that you got this compound from a supplier or whatever, and you want to be certain that you got the correct thing and nothing is wrong. And you record a few spectra. So here we have a proton, we have a carbon, we have an HMQC, we have an HMBC, we have everything. So and we have a COSY also. So how do we proceed here? Well, we just need to do automatic analysis, that is, do the peak picking in all the spectra, and just click the button for automatic analysis, and after a very short time, we get all the spectra picked. And now we can go ahead and do the automatic assignment. I'm going to open this options menu again, and I'm going to disable testing concurrent structures for the moment, and I'm going to say run the assignment. And after a very little bit of time, we get a match factor of 0.95. So yeah, probably the supplier was correct this time. And if I want to add an extra level of certainty, I'm going to say, yeah, test concurrent structures and automatically generate 5 isomers. Let's run the assignment again. And the isomers are generated, and again, assignment is done automatically. And after very short time, we see again, let's close this, we see again a similar result, but different. So our proposed structure is at 95%, and all the other isomers that were generated are at 0. So yeah, we are fairly confident that this is the correct structure. So yeah, that's what I wanted to present in terms of software. I'm going to go back now to the presentation. And in conclusion, there are several possible answers to the what's in my tube question. And each one needs to be tackled in a different way. The database search of known compounds is a very powerful tool for identifying known unknowns. It should not be underestimated. And obviously there are very big advantages in using software tools for structure verification. It's not just the speed and the size of the knowledge base, the larger knowledge base, but it's also the so much higher flexibility and options for eventually coming to the correct answer. Finally, you can never really prove that a structure is correct. You only prove that it's not wrong. Okay, you can't prove that a structure is wrong. Just one disagreement in one of the spectra is sufficient. But you can't prove that it is correct. You prove it only by not being able to prove it wrong. So let's keep this in mind.